Hello everyone. In this video, I will explain what binary coded decimal is. I will explain how a BCD converter works together with a 7-segment controller to display signed fixed point numbers. And finally, I will demonstrate a real-time example of the 7 segments being used to display signed fixed point numbers. So, what is binary coded decimal? Binary coded decimal, also known as BCD, is a format where each decimal digit is represented separately using 4 bits of unsigned binary. The table shown makes it easy to find the BCD equivalent of any decimal digit. A few examples of complete numbers written in BCD are shown below. In the previous video, we introduced the 7-segment IP and explained how it drives the 7-segment displays. For this lesson, the most important input is digits. The digits input contains the 8 decimal digits that we want the 7-segment IP to display, with each digit represented in binary coded decimal. It's best to show an example of how the 7-segment IP works. To make the 7-segment IP display the number 01738801, we must drive the digits input with the number expressed in BCD. The assigned statements below show how to do this using 2 equally valid methods. The method using the hexadecimal radix is better since it lets us type in the number directly. So, why is a BCD converter needed? Arithmetic modules do not normally produce their results in BCD format. Instead, their outputs are represented in signed fixed point format, where A is the total number of bits and B is the number of fractional bits. For example, the multiplier shown below produces its product C as an SSEG number. Since the 7-segment IP expects its digits input to already be in BCD format, the multiplier output cannot be connected to it directly. We must first pass the SSEG result through a BCD converter. So this here shows the entire process. When we have an SSEG number that we want to display, we must first feed it into the BCD converter, as shown below. In the example shown below, the product C is the number to be displayed. The BCD converter will then take the SSEG representation for C and produce a BCD equivalent, which can be fed directly into the 7-segment controller. The other inputs to the 7-segment controller are manually configured by the user. For our real-time demonstration, we will display the number 783.8650 on the 7-segment displays. The fixed point value 783.8650 will be stored in S27.16 format, converted into BCD, and then passed into the 7-segment IP so that the same value appears on the FPGA's 7-segment displays. Alright, so this here is our top level module. On line 21, we have the value 783.8650 represented in S27.16 format. Then below that, on lines 23 to 34, we have all of our signals declared. Next, there is an always block that generates a single start pulse. That start pulse is used to update the BCD converter. Then, the rest of the code instantiates the BCD module and the 7-segment controller. It is important to mention that the Verilog code for the BCD converter will not be explained. The reason is that the main purpose of this lesson is to explain how to instantiate the module and use it in larger systems, rather than how to build it from scratch. The Verilog code is provided in the project files, so you are free to research how it was made on your own if you wish. When we generate the bitstream and program the device, we can clearly see that the fixed point number is shown in the 7-segment displays, proving that the BCD converter is working. If you have made it this far into the video, then you should be able to take the provided BCD and 7-segment IP blocks and use them in your own projects to display any signed fixed point number represented in SSEG format. Alright, that's all for this video, and I look forward to seeing you in the next one.